Hello, welcome to this lecture on LDPC decoding. In the previous lecture, we did some MATLAB coding and we coded the LDPC message passing decoder. If you remember, we did not fully debug it. It was mostly right, and I did some initial debugging. I'll show you some of the changes I made, and then maybe we'll make a few changes and run it and see how it works. Okay, so that's going to be the agenda for this class. Okay. So if you look at this code, I made a few changes. The first change was at this line, at line 10, I had the initialization for the storage matrix for the row processing. That needs to actually move inside the blocks loop, because for every block you have to reset this R to 0. Okay. So that I moved inside this for I equals 1 to n blocks. And the next thing is this Ri needs to be initialized to 0 at the top of every iteration, because when you start a new iteration, it has to start with Ri 0. Okay, so that also I moved inside the while loop. These are the two changes I made. With these two changes, this code pretty much seems to be working. It's giving the expected results. So what I'm going to do is first run through one step by step. I'll run through this code and show you how the whole thing is working. Okay, so let's put a breakpoint here. Okay. So this is something important, you single step through the code to see how it works. So and then if you run it, your debugger has stopped it there, and then you can start single stepping. Okay. So this is loading the base matrix, assigning it to this. We don't expect too many errors here. This is the number of non-minus ones in B, and then you assign a T-reg, and then K and N, rate, EB over N naught sigma, initialize, get into the loop. Okay. So this is message code word, and then the symbol R, L equals R. R has been initialized, and we start the recursion. Okay, start the decoding. Okay, so let's see a few values. Maybe you can see L of 1 colon 32, the first two blocks. So those are the received vectors. Remember, we transmitted the all 0 code word, right? So anything positive is no error, anything negative is error. Okay, so we sent either +1 or BPSK is +1 or -1, and we added Gaussian noise, and you can look at the sigma will be fairly large. Okay, so it's some 0.78, because remember the code rate is really low, right? So if you remember K will be something like 352, N is 1088. Okay, so the code rate, if you look at it, I think I had a rate here which is 0.3. Okay, so it's like 1/3, right? Roughly 1/3. Slightly smaller than that for some reason. So we'll see why that is so, because this is 46 by 68, right? So it's slightly smaller than 1/3. So an EB over N naught of 4 dB and all is quite high EB over N naught, but still the noise will be quite low. This is quite high. Sigma is 0.7848. Okay, so you can expect quite high noise, and you can see so many of the received words are in error. Okay, so look at this, -2. Okay, so that's a lot of error. -0.2, -0.9, quite a few things are in error, quite a few things are not in error on the other side also, but you have errors. Okay, so clearly there are errors, and one needs to see how this can get corrected as we run the iterations. Okay, so if you run more and more iterations, it should hopefully correct it. So you can see here I am going through the row processing, each layer or each block row in the base matrix, and for every block row I am going to try and do the min-sum processing. But for first thing is you have to do the subtraction. The first loop does the subtraction part and row alignment and storing it in this T-reg. Okay, so if you remember, that's what it does. So if you let it run through for the first layer, if you let it run through and run to the cursor, if you can look at this T-reg, it will give you an idea of what's going on. So it needs to have, if I'm not wrong, 19 rows, because there are 19 non-1 in the first block row. Okay, and then each row will have 16 values. These are the aligned values corresponding to the first thing. So for instance, if you look at B of 1 comma 1, it's 10. Okay, and then if you look at L of 1 colon 16, this is the actual received value column aligned. Okay, now this B of 1 comma 1 is 10, so you have to rotate it by 10 positions. And if you look at T-reg of 1 comma colon, it will be the same thing rotated by 10 positions. So it will start at the 11th column So, you can see this is what starts here 0.4274. So, it starts at the 11th column and then it has rotated. Okay. So, this has happened. So, this is T-reg for you. Okay. Now, if you proceed, this loop does the min sum processing, right, and it works just on T-reg, and if you fully finish the min sum, you expect the min 1 and min 2 to replace the value. So, if you go through and look at T-reg of 1 comma colon, so this is not T-reg of 1 comma colon is not where the min sum is run. On the other hand, it is T-reg of colon comma 1. Okay, so first column, remember. So, I rotated the T-reg, aligned it, and then stored it as a row. Okay, 16 values are stored as a row. So, my first column in T-reg is actually the first expanded row in the parity check matrix. Okay, so I have to look at the first column, and on this the min sum is run. Okay, so to look at it a bit more cleanly, maybe I will look at the transpose of this so that we can see it as a row. So, we need to find min 1 and min 2 here, right. So, if you look at it, maybe we can eyeball the min 1 and min 2. 0.42 looks pretty low to me. I do not think there is anything else lower than 0.42 here. So, this should be min 1 should be 0.42, and min 2 looks like is 0.45. Okay. So, min 2 is 0.45 and min 1 is 0.42. Okay, number 1. Now, this is the first thing that min sum calculates. Next is the overall parity. The overall parity is actually minus 1, right. So, there is only 1 minus 1 here. So, if you multiply the signs, you will get minus 1. So, after min sum processing, I am expecting 0.42474 to be all these values. All these other values will be 0.42474. This value alone will be 0.4529, and then all the signs will be flipped. There will be only one positive sign here, everything else will be negative sign. That is what I expect after the min sum. Let us see if that happens. So, we will run through the min sum just for this guy, and then let us say we step and we will see the same thing again. Okay. All right. So, I missed one value as usual, not very surprising. It looks like 0.30585 is min 1, I am sorry. Okay. So, this can happen if you do it by manually. These kind of errors can happen. Of course, the program is not going to make that error. So, min 1 I was totally wrong, it was not 0.42474, it was 0.30585, okay, and min 2 was 0.42474. Okay, and of course, the program has worked on it, it has got the whole thing right. So, you see the whole thing got replaced by 0.30585 except for this guy, which is positive sign, everything else is negative sign, and the whole thing has worked correctly. Okay, so, I am expecting this to work correctly. So, you can finish off the min sum loop and come out here. Okay, and then if you look at T-reg, you will see the min sum has worked. Okay, now, if you look at every column will have only two different values, the minimal value and the next minimal value, and the signs are depending on the overall parity. Okay, so, this is how the min sum has worked. After min sum works, one needs to do the storage back into the R array, and that is what this loop does for you, and then L also gets updated. Okay, it gets added, and then the storage, for the storage you have to do a column alignment, you have to multiply by Z minus B, so that everything aligns properly. Okay, so, this is something you can do, and this will also work. You can try it out, and then you will get message cap. So, if I run to the cursor, I have finished my first block completely. I have done 10 iterations, and you can see message cap. So, is message cap 1 is the question. So, it is all 0, you can go through and check it. Okay, so, it is all 0. Okay, so, you can count that and then see if there are any errors, etc. Okay. So, you can let it run through. I've done this program for like 100 blocks. Okay, so it will run pretty fast. You can run this and you will get the answer. Okay, so this is 4 dB B over N naught, and let's say we continue. It runs for a while. It takes some time, and then it will give you the answer. Okay, so there you go. It gave you all 0, 0, 0, 0, 0. So, now how do you interpret this? Remember, what did we type in here? What did we display here? The display is EB over N naught first, which is 4, and then FER simulated, which is 0, BER simulated is also 0, number of block errors is 0, number of bit errors is 0. So, out of this 100 blocks we simulated, there were no errors at the output. Okay. So, all the errors got corrected by this. It's also maybe instructive to see this L value. This is, remember, this is the total belief at the end of the iterations, 10 iterations, and you can see it's all huge, some 300 odd, and it's all positive. Okay. So, at the decoder everything has worked, and it's also worked really well, and when you say it's 1, you are confident that the bit is 0, there is no doubt the beliefs have really increased to a large value at the end of the iteration. So, maybe we should see this a little bit more, maybe we will see it for a lower EB over N naught. Okay. So, I will keep EB over N naught as 0, and instead of keeping the breakpoint here, I will put the breakpoint here. Okay. So, at this point we will put a breakpoint, and then let us run. Okay. And I want to watch this L of 1:32. Okay. So, this, remember, this is after the first iteration is already over, and you have these kind of beliefs, and remember this is 0 dB. Okay. 0 dB EB over N naught is a sigma of 1.2432. Okay. So, huge noise. Okay. The noise is been added a lot, and if you see R of 1:16 or 32, if you will, that is the received value. Received value is it's got quite big values, and it will have big errors also. And if you see L, it's that's what happens at the end of the first iteration. So, then the first iteration, it looks like there's still errors. Okay. Now, we can continue this, and you get the second iteration, you can see ITR is 1, well, it's not been incremented yet. The second iteration, you can see L. Okay. There are more negative values, things are not looking very good, maybe there's -4 and all that, looking a bit scary. Let us continue again, maybe 0 dB is too much noise. Okay. Let us see, we are doing 10 iterations, you never know what can happen. Let us continue again, maybe this is some good news, I am not sure. Let us continue again. Okay. So, errors can happen, it can happen that there are some errors that you do not correct, and you will go through and see how it is. So, but this is an instructive way of seeing what is going on. So, you see some of the bits are becoming very reliable, right, 10 and all that, but some bits are still lying out there, minus, these are all errors. Okay. Anything negative is an error. Okay. So, 0 dB EB over N naught for this code, maybe at this block length, it's not very good. Let us see that. So, if you want to fully continue, you can do that out here, and maybe I will clear this breakpoint and then run to cursor. Okay. So, it ran the whole thing, and you can see the final update in L, there is still some negatives. Okay. There are still negatives. So, this will be an erroneous block. Okay. So, this is something you can see. So, the errors can happen if you reduce block error rate, errors can happen, and okay, I am going to quit debugging here, but maybe we will run this at 0 dB EB over N naught, see what it does. 8 iterations we did. Okay. And for 100 blocks for this rate 0.32 or something code, block length is not very high. So, you see every frame was an error. Okay. So, there were 100 block errors, but not every bit was an error. The bit error rate was 0.28, not too bad. Okay. So, that is the situation with EB over N naught of 0 dB. So, maybe we do 1 dB, let us see what happens. Okay. So, this is taking a little time. So, you see there is a lot of value in writing more efficient code if you want quick answers. So, for instance, okay. So, anyway, so let me finish the simulation for you. At 1 dB, you are already seeing that there are 8 blocks that got corrected, so which is good news. So, 8 iterations is good. So, one more thing worth trying is maybe we want to try 16 iterations, right. So, it will take a little longer, but it is worth seeing. This also tells you that there is a lot of scope for improving the efficiency. For instance, this loop is very badly written. Okay. So, those of you who know MATLAB code, you will know that this loop is very badly written. I can very easily cut this short significantly. Okay. So, because the same loop comes even here, right. So, this loop can be speeded up, we will speed it up maybe in the next time we run it, but you see here when you did 16 iterations, already there was some improvement. Okay. Remember, this is not the same 100 blocks, this is another 100 blocks, but out of 92 errors, 92 out of 100 were in error here 81 out of 100 were in error. The fraction wise maybe not a big difference, 0.8, 0.9 is pretty much the same at this kind of thing, but there is improvement. Okay. So, there is merit in doing some more iterations. So, but we will keep the number of iterations at 8, I do not want to do more than 8. Maybe we will increase the EB over N naught to 2, and let us see what happens. Okay. So, in the meantime, let us think about how this loop can be speeded up. Okay. So, I am running it through 1 to NB, and I am running this loop only for those columns which are not -1. So, a very easy way to speed this up is to do the following. So, you run call to be equal to, okay, not 1 colon NB, those values of b of layer comma call which are not -1. Okay. So, one very easy way to do this is to write this for this guy. Okay. Find of not -1, and then you have gotten rid of one loop. Okay. So, this what does this do here? So, it looks at b of layer comma call, sorry, colon, I should change this to colon. It looks at the whole row, the layer block row, and see where all there is no -1, and simply loops over that. Okay. So, this is a very quick way to cut short this little loop here. I can do the same thing here. Comma colon, and then I get rid of this. So, this should be a little bit faster. Okay. And hopefully, I did not make any mistakes. So, let us run it again and check this. Okay. So, there were 38 errors this time. So, that is okay, 28, 18, it is not a big deal. Run it again. Hopefully, this was a little bit faster, not sure. Okay. So, anyway, loops in MATLAB are not always the best thing to do. So, you need to figure out how to do this differently from without loops. So, in fact, it is possible to write without all of these loops. Okay. So, you can write some very efficient MATLAB code, but we are not trying to do that much here. So, anyway, it is good, this is fast enough for us, it is not too bad, we can work with this. So, this gives you a 2 dB, it gives you a certain block frame error rate already, which is 0.22, okay, and then slowly it will start falling at 3 dB of EBOR and not and all that, it will start falling to lower numbers. Okay. So, hopefully, this is expected performance. I am not sure if this is really good. I will have to check this, because it looks like this code should do something slightly better than this, but maybe the expansion factor is very low, but at least at high SNR it works. I will check on this once again, and it should be fine. Okay. So, maybe we need to change this to some other base matrix. So, let us see what all base matrix we have. So, if you look at 1 0, it goes all the way up to 256. So, let us try 1 0 256. Okay. So, this will take a little longer to run. Okay. I do not think I need to make any other change here. This should just work. This will be a much larger block length, but nevertheless, we are keeping the base matrix the same. So, the complexity of this should not be very high, I think. So, let us run this. Okay. Okay. So, I made a mistake here. I should load 256 here. Okay. So, let us see, this is a much larger block length, and let us see if this works correctly. So, you can see it is taking a little bit of time. So, generally LDPC codes at larger block lengths will perform much better. Okay. So, block length of 1000 is a bit low for LDPC codes. 2000, 3000 and all, they are very difficult to beat. They are really very good. They give very competent performance. So, 256 is a pretty huge block length, you can imagine. So, this program will take a little bit longer, but let us see 2 dB EBOR and not 256, does it give you significantly better performance than before. Okay, let us see. I am sort of expecting 0 errors here. Let us see. Okay, so you can see there was just one error here. Okay, out of 100, that actually looks quite wrong to me. This should be much better than this. So I am not sure if maybe this is expected performance. So, I will look into it a little bit more, compare with some literature and confirm whether this is good or not, but I think it should be good. It looks all right to me as far as the code is concerned. I do not think there is any big mistake. Okay. A few changes that usually people make to this code. The first change is rate matching. Okay. So, you have to do rate matching. So, this always simulates the lowest rate that is there but that's not how transmission happens. Okay, so you have to do some rate matching. That's the first thing. The other thing that people do is you want to do you want to quantize the received value. Okay, so at this point you can see, so I'm doing AWGN channel, right? So and I'm using the real value itself as L. Okay, so that's not very nice. So you want to quantize this, okay, to how many ever bits or integer values between say minus 256 and 256 if you want to use 8-bit integer values. Okay, so that's something very important. You have to quantize. Number one, like I said, number one was rate matching. I'll talk about it in the next lecture, and after that quantization, which will also be there hopefully in the next lecture. And the last step is changing this step to to offset min sum. Okay, so instead of doing min 1, min 2, you want to subtract a small offset here. Okay, so all these three we'll do in the next lecture and see how much it improves or how the performance changes. Okay, so other than that, the basic algorithm is as such okay. Okay, thank you very much.